Did you know today just two relatively short questions. Number one, draw the resulting solution when KCl is dissolved in water. Be sure to show the interactions that occur during the solvation process. So KCl, potassium chloride, is ionic. So KCl is ionic. When we put KCl into water, since it's got potassium, since it contains K+, it will break apart. So KCl, I'm just going to write the equation, KCl will dissociate into K+ and Cl-. And so what number one wants us to show is how the water molecules surround both of the ions. So this is similar to, I looked at a question yesterday or a couple days ago that looked at the ions, I think it was Monday, Tuesday, whatever day you guys were here last. Okay, Tuesday. With water molecules surrounding the ions. So I'm going to have K+, and then remember in terms of ions, cations are smaller, anions are larger. So as long as you show K+ being a little bit smaller than Cl-, then we're going to show the water molecules surrounding each of them. So we have to make sure to orient them the correct way. So with water, water has a partial negative side and a partial positive side. It doesn't matter to me whether you want to represent H2O like this, right, like the Lewis structure, or if you want to do H2O. This represents the same thing. Just remember, it's one O and two H's. I say that and you're like, well, duh. You'd be surprised how many people actually say H and two O's. Right? So whether you want to represent water as the Lewis structure or using this little structure, either one works. So when we focus on the waters surrounding potassium, since potassium is positive, the partial negative side of water will attract to K+, because opposites attract. So the partial negative side is oxygen because it carries those lone pairs of electrons. So I'll represent it. I'll do K+ using the little models of water. So for K+, notice how all of the oxygens orient themselves facing toward the K+. Think about like the magnets that we looked at before. If I tried to put the hydrogen toward K+, they're the same charge, that will repel. And then for Cl-, so if I wanted to represent it using the Lewis structure, it might look like this. And so there's water with the hydrogens facing chlorine. Hydrogens facing chlorine. So then it would just look like this. And again, I'm just showing both. So that way, whichever way you did it, whether you did it with the Lewis structures or with these structures, they both are acceptable, but notice how the oxygens face toward potassium no matter what, hydrogens would face toward chlorine no matter what. So in terms of the interactions, just to review really quick, notice how there's no bonds between the water and the Cl. I'm not showing any solid lines. Those are covalent bonds, right? These are covalent bonds inside the water molecules. But if we want to talk about attractions, between the ion and the polar water molecule, this represents ion dipole forces. And the ion dipole forces, that's why we can form solutions. So it'd be the same thing, like the hydrogens attracted. Notice it's dotted lines though, and I'm trying to make them really light, just to show that it's an attraction. It's not a bond, it's simply an attraction. Just like the magnets were, it's an attraction between two different substances, but these ion dipole forces are relatively strong. And so these are strong enough that we can separate the K+ and the Cl-. So we actually can break the ionic bond and form this solution because of these ion dipole forces. If you think about the name ion, Here are ions. Dipole means it's polar. Water is polar. So ion dipole is an attraction between an ion and a polar substance. It could be something else besides water. It could be HF. HF is polar. So if you have an ionic substance and you dissolve it in HF, that would also be ion dipole forces. So that just shows that solvation process, dissolving something in water. Number 2, what type of solid? So let's first just focus on what type of solid is MgNO3-2. So your types of solids, you have molecular, covalent network, metallic, and ionic. So what type of solid would magnesium nitrate be? So molecular is all nonmetals. Covalent network is really only elemental carbon and SiO2. Metallic is pure metals, and ionic is metal and a nonmetal, right? Or metal and a polyatomic. This is a metal and a polyatomic ion. This is an ionic solid. And then I said what type of attractions hold it together. So if you have an ionic solid, we just talked about it up here, right? It's held together with ionic bonds. So when you're looking at types of solids, you really are focusing on, is it molecular, covalent network, metallic, or ionic? Metallic has to just be a pure metal. Copper, zinc. Unless it's an alloy, it's going to just be a pure metal. Covalent network, you really only have 3 possible covalent network solids. So really you're looking between molecular and ionic. Molecular is all nonmetals, ionic, metal, nonmetal. Questions on the do now? Nada? Okay. So before we get into, I'm using this computer today. Before we get into free response questions, so I want to go through most missed questions from both of the quizzes. So the Chapter 11 quiz scores were released a while ago. right after the quiz, I released the scores. If you can't find the email that has your Chapter 11 quiz score, if you send me an email, I can re-release the score to you. But make sure you send me an email, because if you tell me right now, I'm going to forget. And so these were the 2 most missed questions from the Chapter 11 quiz. We'll go over the most missed questions from yesterday's quiz. I released yesterday's scores yesterday afternoon. So you could go back through, you can look at the feedback. I go in, even though it's in Google Forms, and I type feedback for every question. So if you miss a question, you can go back in and you can see what was missed, why did you miss it. You'll notice on the Chapter 12 and 13 quiz, a lot of people missed one question, and I think it was because of the wording, just not necessarily reading it as carefully. So for Chapter 11, remember Chapter 11 was all about intermolecular forces and properties of liquids. So looking at vapor pressure, boiling point, tying it back into intermolecular forces. The first question, solid carbon tetrachloride, CCl4, is represented by this diagram. So this is just showing multiple molecules of CCl4 close together that represents a solid. What are the attractions between the CCl4 molecules that hold the molecules together? So when you're looking at questions like this, now remember these were all multiple choice. I just needed to save space, so I'm just making it into short answer. So what are the attractions between the CCl4 molecules? Between molecules is intermolecular forces. It wants to know what are each of these dotted lines. Those are intermolecular forces. It doesn't want to know about these bonds. That's not what it wants to know about. It wants to know about the attractions between. Those are intermolecular forces. So then what you need to do is you need to ask yourself, okay, so is it polar, nonpolar, ionic, and how to figure out the intermolecular forces? So CCl4, well, they show you what it looks like. You have carbon in the middle with 4 chlorines. So if you have carbon in the middle with 4 chlorines, it's a perfectly symmetric molecule. CCl4 is nonpolar. So CCl4 is nonpolar. The only intermolecular force that can exist between two nonpolar molecules are London dispersion forces. So when you are looking at intermolecular forces, remember inter means between. So intermolecular forces are looking at all of these attractions, not bonds, but attractions. So you're looking at, is it dispersion? Is it dipole-dipole? Is it hydrogen bonding? Is it ionic bonds? And it's based on if the molecule is polar or nonpolar or ionic. So this first one was London dispersion forces. The second one, equimolar samples of CH3OH and C2H5OH are placed in separate containers. Compared to the vapor pressure of CH3OH, what is the vapor pressure of C2H5OH? So this was multiple choice, and it said like higher because, lower because. You had to pick it and give the right justification. So it wants to know if we are looking at, right, we give this a certain vapor pressure. So this is, vapor pressure is X. It wants to know how will C2H5OH's vapor pressure compare? When you're given a table like this and it has specific data, use that data to help you figure out properties. Vapor pressure is based on intermolecular forces, just like boiling point. So essentially what we want to do is we want to use boiling point to compare the intermolecular forces, because really this is asking, how do the intermolecular forces of C2H5OH compare to CH3OH? So we have methanol and ethanol. Ethanol has a higher boiling point. A higher boiling point means stronger IMFs. So a higher boiling point means stronger IMFs. So if we're comparing these two, ethanol will have stronger IMFs, methanol will have weaker IMFs, just based on the boiling point. So if ethanol has stronger intermolecular forces, it wants us to relate that to vapor pressure. So remember that vapor pressure is the pressure that exists due to the gas above the liquid. I drew a lot of liquid in that container. Right, so it wants to know, what will the vapor pressure of C2H5OH be? If these liquid molecules have strong intermolecular forces, that means they are very attracted to each other. All right, let's use this classroom as an example. All right, if we were allowed, and you guys all like linked arms, right? That's really strong attraction. It's really hard for one of you to escape the classroom because you all have linked arms. You have strong attractions. So if you have strong attractions, if a liquid has strong attractions, there's not as much gas above the liquid. Well, if there's strong intermolecular forces and there's not as much gas up above the liquid, that's going to result in a lower vapor pressure. So the equilibrium vapor pressure of C2H5OH is going to be lower than CH3OH because C2H5OH has stronger intermolecular forces. It takes more energy to allow those liquid molecules to escape. So everything in Chapter 11 came back to intermolecular forces, and even some of Chapter 12 goes back to intermolecular forces. Unfortunately, intermolecular forces are not going away. Sometimes we'll relate things back to IMFs. But all of Chapter 11 was on intermolecular forces. 12 and 13. So this is from yesterday, so these questions might look familiar, or maybe you just tried to completely forget about it. If so, okay. So there were 3 questions. This first question was the most missed question out of both quizzes. I think it was something like 2 or 3 people in this class got this first question right. It was only like 10% of everyone got the question right. And it wasn't because you didn't know what you were doing, it was because of how the question was asked. And again, all of these are old or practice AP multiple choice questions. So this first one, what is the volume of distilled water that should be added to 10 milliliters of 6 molar HCl in order to prepare a 0.5 molar HCl solution? So based on the answers that I saw, everyone knew this is a dilution problem. Right, so based on the answers I saw, everyone knew this was dilution because you had HCl and you were just going to a different concentration of HCl. So that's just, and you're adding distilled water. So 6 molar, 10 milliliters, 0.5 molar. And when I solve for V2, it's going to be in milliliters as well, because your units will be the same. So remember, you're getting a calculator on everything. So 6 times 10 divided by 0.5. This was the answer that most people chose. But notice I didn't box the answer. This isn't the final answer. Once you realize why, you're going to be like, oh my gosh. What is the volume of distilled water that should be added to 10 milliliters? So the final volume is 120 milliliters. All right, that's the final volume of solution that we need. But the question says, what volume of distilled water should be added to 10 milliliters? So if this is your final solution, that means you need 110 milliliters that is added to 10 milliliters to make the solution. So most people actually chose 120. So that's why I said most people, they knew it was dilution. It was just this added to part of the question. The second question, so this was looking at ionic solids. So why does NaCl have a lower boiling point than NaF? And then it said use these tables. So it gave you these tables, and then it asked about the boiling point of ionic substances. So NaF has a boiling point of almost 1700 degrees Celsius. Then they give us these ionic radii. These are both ionic. For ionic substances, so whenever something is ionic and you are looking at properties, boiling point, melting point, even the attractive forces, so even the strength of the ionic bonds, we have to actually go back to Coulomb's law. So remember that Coulomb's law looked at the charge and the ion size. So when we're looking at boiling point, remember boiling point is essentially just the strength needed to break the ionic bond. So when we're looking at boiling point, we have to go back and look at Coulomb's law. So if we look at NaCl versus NaF, well, if you look at F and Cl, Cl is bigger. So if I look at drawing NaCl, so I have Na plus Cl minus versus Na plus F minus. Cl is a much larger ion. And so since it's a larger ion, the attraction between the nucleus of Cl minus and the nucleus of Na plus is not as strong. Farther away, the larger the distance, less the attractive forces. So NaCl has a lower boiling point because the attractive forces are not as strong because Cl minus is a larger anion than F minus. So the further apart the nuclei, the weaker the attractive forces, the easier it is to break. And then finally, this third one. So this third one wasn't missed. I mean, I was just trying to pick the third most missed. I think it was still like 60% of everyone got this question correct. But how many moles of Na plus are 100 milliliters of 0.1 molar Na3PO4? So what it looked like based on the answers, if people got it incorrect, is they just went, okay, there's 3 ions, I'm just going to multiply this by 3. That would be the concentration, that would be the molarity of Na+. We want moles. So what I would suggest doing, and I'll just work through it up here, I'll work through it up here so everyone can see, is I'm going to say, all right, I'm going to start by solving for moles of Na3PO4. So if I have 0.1 molar, X moles is 0.1 liters. Is that 0.01? I think it's 0.01. I'm just going to double check. 0.01. So X is 0.01 moles of Na3PO4. Now I want Na plus. Now you can look at that ratio. For 1 mole of Na3PO4, there are 3 moles of Na plus. So our answer is 0.03 moles of Na plus. So you just have to be careful and make sure that you're solving for the correct variable as well. I always would suggest if it wants moles of something else, start by using your information and solve for moles of what you would know. So in this case, solve for Na3PO4, and then you can use that ratio to find moles of something else. But again, this first question was the most missed question out of both quizzes. And it was because of that added to term. So it wasn't that you guys didn't know how to do dilutions, it was just the way that AP worded that question. Any other questions? So again, I released both of the quizzes already. This one just got released yesterday. So if you can't find the email or something, send me an email so that I have it and I can literally just use that, go in, release your scores. And it comes through your email. It says something like score released and then the name of the quiz. You can click on it, you can see all the feedback. You might be able to click through it in Google Classroom. I'm not sure. I think some people may have been able to go through Google Classroom as well. So just a couple other things. So some additional review resources. I have put some things up here, and this is in the do now slide. So if you want to go back in, if you remind me tomorrow, like when you guys are on Google Meet, I can send you these links as well. But I just put together some different resources all on one slide just to help, because this is a big unit. Right? This is 3 chapters. At the end of the chapter 11 and 12 notes, there was something that says what you need to know. And I don't think it got on chapter 13 somehow. That page was left out. So I put all of them on one Google Doc. So remember, I only ask questions that AP tests on. So this what you need to know, these are all of the concepts from chapters 11, 12, and 13. Basically all of the general information from those chapters. So that is all in one Google Doc. Separating liquids, so if you want to go back and you want to look at the Google slide deck from when we went through separating liquids, that link is here. And then there's also kind of a general information, I'm not even going to call it a sheet, because it's like an extra notes packet almost, that it's like a national science foundation that does some work with AP. And so I have this as well. This really just focuses on intermolecular forces. So if you need to go back and review IMFs in a little bit different way, I have that linked here as well. So these are just 3 additional things. If you want to use them, great. If not, okay. I mean, you need to know the separating liquids, so that's there. And then posted on the class website, the review packet, the answer key for response questions, for response answers, old review packets. That's all on the class website as well under Unit 4 review. So just lots of information just to help review. As always, if you're working through and you're reviewing and you have questions, even over the weekend, send questions. And if I don't answer them like right away, I'll probably answer them within an hour, I would say. We're going to start Unit 4 free response questions. So there are 8 questions total in this entire packet. We're not going through them all today, so we'll continue to work on them tomorrow. Tomorrow we'll do an additional review as well. And we'll work in small groups. So what I'll do, we're getting smaller and smaller, is you guys can pick, some small groups to work in. You'll have, we'll probably have, we could have 2 groups of 4 even. And we'll go through, we'll time them just like we've been doing. I'll put the answers up on the board. We're going to go ahead and go through the answers to this question. Again, you can see it was from 2017. This was number 4 on the 2017 free response test. So questions 4, 5, 6, and 7 are considered short questions that should take between 7 and 9 minutes. Now you might notice that this question did not take you 7 minutes. Right? That's okay. Some might take you a little longer. So for this question, this is a chromatography question. This is why I made sure that we did the chromatography lab this year, because there have been free response and multiple choice questions about chromatography. So they give you this information. Now what's important to notice about this chromatography question is that the solvent is non-polar. So the paper is polar, the solvent is non-polar. So if something is more attracted to the solvent, it's going to actually be non-polar. So it's opposite of what we did in class. And then they give you the chromatograms. So for these 2 questions, and you can see exactly how points were awarded. So short questions are worth 4 points. For part A, which dye, A, B, or C, is the least polar? Justify your answer in terms of the interactions between the dyes and the solvent, or between the dyes and the paper. So it tells us exactly how we need to make sure to justify our answer. So in order, or to answer the question on which dye is the least polar, we need to say dye C. C is the least polar. So we got 1 point on this for saying dye C and referencing the chromatography paper. So dye C is the least polar because it moved the furthest. That was one of the points. The second point came from talking about either the dye to the solvent or the dye to the paper interactions. So notice here it says and or. So we could say it is either dye solvent or dye paper, or you could have said both. So the nonpolar dye is more strongly attracted to the nonpolar solvent, which is why it moves the furthest, or the nonpolar dye is least attracted to the polar paper, so it's not going to stick to the paper as easily and it's going to move up further. So either one of those explanations, but notice it says and or, so you have to have one of these talking about the dye's interactions to either the solvent or the paper. And then part B, which dye is present in the unknown sample, justify your answer. So you got 1 point for saying dye A. You got 1 point for saying dye A is the unknown in the sample, and then it says justify your answer, so the second point came from the justification. If you take a look at the dyes, so notice the solvent front. Right, the solvent front has moved up further on the paper with the 3 dyes than with the unknown. So remember when we did chromatography, we calculated what was called the RF value, and that was when you took the dye divided by the solvent front. Well, you can, whether you want to talk about RF factors or you want to talk about just the location of the dye in reference to the solvent front, either one of those would work. But for part B, you need to provide one of the following justifications to get that second point. So the unknown sample moves about halfway between the starting point and the solvent front. and dye A also moved halfway between the starting point and the solvent front. Or you could talk about the RF value. Right? The RF value is about 0.5 because it's halfway up the paper, and dye A has an RF of about 0.5. So either one of those works, but this was a 4-point question. So in terms of scoring for this question on the 2017 test, so you could see how you would score out of 4. Please know, it is not, if you get like a 4 out of 4, that's great, that's awesome. The average, right? The average is usually about those that get a 3 on the test. That's an average. The average on this question was a 1.78 out of 4. So if you got a 2 out of 4, you got a 3 out of 4, or even a 4 out of 4, you were well above the average. Right? So it's not like you have to get an 80% or a 90% to get a 5. The average is a 3. On this question, a 1.78 out of 4 was the average. Right? So we're going to just, well, let's see. Let me see if there's a quick question. Because number 3, well, I'll just kind of add the time in. Number 3 is a long question. So number 3 is considered a long question from the AP test. So notice how it's 2016. Number 3 looks like this. This is almost the entire long question. And so this I'm going to give you 15 minutes for. So we'll go through the answers to number 3. So I will tell you this was not the entire number 3. So you're going to notice that there are 7 points possible. Long questions. So questions 1, 2, and 3 of the AP tests are always long questions. They are worth 10 points. This only shows 7 of the points. So the other 3 points we just haven't talked about yet, so I didn't put it on this packet. So for part A, it says given that the metal M is in excess. So that means you have a lot of it. You don't have to worry about it affecting the stoichiometry. That means that I2 is the limiting reactant. Calculate the number of moles of I2 that reacted. So I didn't put, here, I'll show you this. I did not put this entire picture on the scoring guidelines, but I do want to show you up here at the top, you have a balanced equation. That's going to be useful. Then you have this data table. So this data table gives you a lot of information as well. So you have the metal plus I2, you have the beaker plus just the metal. So if you subtract those, that will give you the mass of I2 that reacted. So 1.021 grams of I2 reacted, and then you use the molar mass to go to moles. So part A was just 1 point. Part B, calculate the molar mass of the unknown metal M. Molar mass is grams per mole. So if we need to find the molar mass of something, you actually did this in the gravimetric analysis lab, and I know that was a long time ago, but the molar mass means you need the grams of M divided by the moles of M. And so what we can do first when we're looking at moles, based on that balanced equation at the top, M to I was a 1-to-1 ratio. So the moles of I2 equals the moles of M. Now, if you got part A wrong, but you used your number from part A on the denominator, you still could get part B. So part B was worth 2 points. So one of the points came from the number of grams of M. So where they got these, like this calculation, 1.284 grams of Mi2, if you looked at the data table, that was the mass after the second weighing. So that's when all of the water has been evaporated. Then they subtracted I2. So the law of conservation of mass says that mass is neither created nor destroyed. So if you have a sample of Mi2, it consists of M and I. Well, you know the mass of I2 from part A. So you subtract them, that gives you grams. You got 1 point for the correct number of grams. Let's say you're like, I don't know, I'm going to make up a number and make it say 1. You would miss that first point, but if you did 1 gram over the moles from part A, you still could have gotten that second point. So grams over moles gives you the molar mass, 65.4 grams per mole. Now, this was really the most important part of this free response question, was looking at properties. So the student hypothesizes that the compound formed is ionic. So part C, propose an experimental test the student could perform that could be used to support the hypothesis. Explain how the results of the test would support if it was ionic. So this was 2 points. 1 point for having a correct test. The second point from saying how the results would tell you if it's ionic. So either one of these would work. We've been talking a lot about this first one. You can tell that something is ionic if it does not conduct as a solid, but conducts when it is melted or in solution. So the student could dissolve the compound in water or melt it and see if it conducts. If it conducts electricity, that means it's ionic. Or you could say that the student could test the melting or boiling point, because ionic substances have very high melting and boiling points. So if you test the melting point or the boiling point and it's very high, it's most likely ionic as well. So that was 2 points, right? 1 for giving one of those tests, and then 1 point for saying how you could tell that it was ionic. And then part D, so this is going to intermolecular forces. So this is why I said part C and D are probably the most important parts of this free response question. Explain why I2 is a solid at room temperature, whereas Br2 is a liquid. Your explanation should clearly reference the types and relative strengths of the intermolecular forces present in each substance. In each substance means you need to tell what type of IMF is in I2, what type of IMF is in Br2. So if you think about both of them, I2 and Br2 are both nonpolar. So both Br2 and I2 molecules are nonpolar, so the only intermolecular force for both is London dispersion forces. Whether you say London forces or dispersion or LDFs, they will know what you mean. So that was 1 point, just for saying that they both exhibit dispersion forces. Then the second point comes from the explanation. So remember that if I2 is a solid, solids have stronger intermolecular forces than liquids, which have stronger intermolecular forces than gas. So if I2 is a solid, that means that it has stronger IMFs than Br2. So we could say that the dispersion forces are stronger in I2. Remember, with dispersion, you talk about the electron cloud. So we could say that the dispersion forces are stronger in I2 because it has more total electrons, giving it a more polarizable electron cloud. And that would give you your second point. So this question, this is only 7 of the 10 points. But I can tell you that the average on this entire question, so remember we're missing 3 of the points. The average on this entire question on the 2016 test was a 3.83 out of 10. If you got part C and D, you beat the average. Right? So this is why we do free response questions. So you get used to doing them and seeing that it's okay to not get every single point. Right? The average out of 10 was a 3.83. So we're going to do just one more question for today. So I want you to flip to question number 6. So question 6 starts on page 5 and continues on to page 6. So there's parts A, B, and C. We're going to do 9 minutes for this question. So this is going to go back to intermolecular forces. So we're going to do 9 minutes for this question. So this is the last question that we'll go through together. Tomorrow we will do numbers 7 and 8. And then that's all we'll go through. But I wanted to make sure we hit one of the intermolecular forces questions each day, just to make sure that in person we can talk a little bit about it. So for number 6, answer the following in terms of principles of molecular behavior and chemical concepts. So part A, they give us glucose and cyclohexane. So glucose is the one that has oxygen in it. Cyclohexane is just C6H12. So it says identify all types of intermolecular attractive forces in glucose and cyclohexane. So glucose, everything has dispersion forces. But if you notice how glucose is bonded, you have these OH groups. And when you have hydrogen covalently bonded to NO or F, it has the potential to multiple bond with other molecules. So glucose is able to have dispersion forces, dipole-dipole forces, and hydrogen bonding. Or if you just said hydrogen bonding and LDFs, that's fine as well. But remember that hydrogen bonding is just a special type of dipole-dipole forces. The second one with cyclohexane, all C's and H's. This is a perfectly symmetric molecule, and so the only IMF is London dispersion forces. Part B says glucose is soluble in water, but cyclohexane is not. Explain. So remember, solubility is about the attraction between the two different molecules. The stronger the attractions between the two molecules, the more soluble they are in each other. So for glucose, the OH groups in glucose can form strong hydrogen bonds with water, so glucose is soluble in water. If all you said was that glucose can hydrogen bond with water, that's an acceptable answer as well. However, cyclohexane cannot form strong attractions with water because it only exhibits dispersion forces, so it's not as likely to be soluble in water. And so the way that was scored, 1 point for talking about glucose, 1 point for talking about cyclohexane. So it's really important that you make sure that you're talking about every topic covered in the question. Then part C says, consider the two processes represented below. So process 1 is liquid water going to gaseous water, and process 2 is water decomposing into hydrogen and oxygen. So it says, for each of the two processes, identify the type or types of intermolecular attractive forces that must be overcome for the process to occur. So in process 1, because it is simply water undergoing a phase change, we just focus on the intermolecular forces. So for process 1, hydrogen bonds, or if you said dipole-dipole forces, in liquid water must be overcome to allow for a phase change. So it was 1 point for identifying process 1, 1 point for identifying process 2. In process 2, water is breaking apart into molecules. So in process 2, the covalent bonds must be broken to allow water to break apart into H2 and O2. So process 1 is hydrogen bonds, an intermolecular force. Process 2, we have to break covalent bonds. Process 2 is a chemical reaction. Process 1 is simply a phase change. And then finally, part 2 asks you to agree or disagree. And so it gives you a statement talking about water boiling. So it says, when water boils, H2 molecules break apart to form hydrogen molecules and oxygen molecules. And so you need to indicate whether you agree or disagree and then support your answer. So you can't just say I agree or I disagree. You need to then elaborate. So hopefully you said that you disagreed with this statement. When water boils, water is simply undergoing a phase change. You are only overcoming intermolecular forces. So you should say you disagree. Boiling is just process 1, so you can refer back up, in which only intermolecular forces are broken. Water, it's still water. No intramolecular force, no covalent bonds are broken, only intermolecular forces. So water is not breaking apart to form hydrogen and oxygen when it boils. It's not simply undergoing a phase change. Okay, so that was it for number 6. Again, we're going to do 7 and 8 tomorrow.